guess what? If the door wasn't there, if you were here and you weren't strapped in and the door wasn't there, guess where you would go? You would go out the door. You would go immediately out the door. There's nothing holding you back. And actually, you wouldn't feel any force at all because you would be traveling and your motion would just project you out. And you'd find yourself outside of the car, and the car is going on around you. But fortunately, you're locked in, and there's a side of the door there, and you hit the side of the door, and you feel what we call, oh, the centrifugal force threw me to the outside. Really, thank goodness it did, because the door catches you, and you go along with the car. The door is actually supplying for you and the car the centripetal force to keep you going around the circle. If that door wasn't there, you would feel like you're being thrown to the outside. And so that's why we say it's really a fictitious force. It's not a force at all. It's just a reactive force of, it's the reaction of what you feel as you're thrown to the outside. Again, if there's no door there, you would go outside the car, and the car would leave you behind. Okay? But the door catches you, and you say, oh, you would say the centrifugal force has thrown me to the outside. There was no, actually, it didn't throw you to the outside at all. It's just that here, you're not strapped in. If you're right here, you're not strapped in. As the car continues that way, you continue straight and you slam against the car door. Okay, you're traveling in a motion, the car's traveling circular, and you hit you hit the side of the door. There's not really any force at all involved with that. Do you understand? So, I hope that clears that up. Okay, if we go over to page 230 now, we're going to talk about gravity. Okay, and just Isaac Newton came up with gravity, and the gravitational force, we say the force of gravity, the gravitational attraction between two masses is G, we'll call it today, what do they give it the, yep, symbol big G, M1, M2, divided by R squared. Okay, and this is, of course, this is, it was Isaac Newton who developed this, and this is one of the reasons why he's so famous, in particular to the Newton's laws of motion, or Newton's three laws. And it is true that in order to come up with this, he struggled with this for some time, and he actually had to develop or invent calculus. What he was doing is he was really studying the motion of the Earth and the Moon. He was looking at, he was in the Sun, but in, the Earth and the Sun, how these orbited by each other, but in particular how the Moon orbits the Earth. And he was studying this, and in order to figure all this out, he had to look at the entire body of, the Moon is like a ball, and the Earth is like a ball. And so it's a solid mass, and so he's had to study all, in order to take all of the account for the entire mass inside this ball of the Earth, he had to use calculus. And it turns out there are two people about the same period of time that actually pretty much independently, we think, invented calculus. There's Isaac Newton, and then there is a German mathematician called Leibniz. Leibniz, I think I spelled that right. more or less the same time period as Isaac Newton, and he developed calculus also pretty much independently, as much as we know from history. And however, if you look at the form of the calculus that we use today, and you compare it with what Newton did and with what Leibniz did, it turns out the form of the calculus that we use today is really more akin to what Leibniz used. Isaac Newton's form of calculus, it worked fine, but the form his form was a little bit more maybe archaic, if you will, and so we don't do calculus typically the way that Isaac Newton did it, just because we're so used to doing it the way we learned it from Leibniz. So just a little bit of history there. But what does this law say? If we have two masses, m1 and m2, and they're separated, let's say from the center to center of a certain radius, that there's a gravitational attraction between these two. Okay? And this gravitational attraction pulls these two masses together. We'll call it F sub g. F sub g. In fact, it's an equal pull. This mass is attracted to, m1 is attracted to m2, and m2 is attracted to m1 by the equal but opposite force. Now remember Newton's third law. For every force, there's an equal and opposite reaction force, and that's true of gravity. This mass, this is Newton's third law, which is important. There's a force here directed right to the center, just like there's a force here directed to the center of this one. So there are each reaction forces to each other. Okay. Now G, if you look in the front of your book, you'll see there's some physical constants here. And if you look at big G at very bottom here, G is defined as, it's a constant, 6.67 times 10 to the minus 11, and it's Newton times meter squared per kilogram squared. Okay, so it's a very small number. Okay, for an example, suppose M1 was 10 kilograms and M2 was, let's say, 50 kilograms. And the radius here was, let's say, we'll just make it, to make it easy, make it 1 meter. Okay, so two masses just separated by about 1 meter. Okay, what would this force numerically be? Let's go ahead and calculate it. Force of gravity between these two masses would be 6.67 times 10 to the minus 11 Newton times meter squared, or divided by kilogram squared, times 10 kilograms times 50 kilograms divided by 1 meter squared. Okay, so if you take out your calculator, and we calculate that, 6.6, so here's where you have to use your scientific notation, 6.67 e to the minus 11 times 10 times 50 divided by 1, and I get 3.33 times 10 to the minus 8 newtons. Okay, that's a very, very small amount of force. Consider, for instance, the weight of this 10 kilogram. Well, heck, let's look at the weight of this mass here. remember the weight equals m times g. We would have 50 kilogram times 9.8 meters per second squared. So the weight of this mass alone is 50 times 9.8, 490 newtons. So this weight, the weight of this mass is 490 newtons, and it feels a force of 3.33 times 10 to the minus 8. That's about 10, let's see, 3 orders of magnitude, that's about 11 orders of magnitude smaller than the force of than the force of its weight. So essentially, it's very, very, very small. So two masses like this, okay, they would be attracted to each other, but the force of attraction is so small that just the slightest amount of friction will keep them apart. Okay? Now, you may say, well, what if you had these two masses out in space where there was no gravity around them? Would they be attracted to each other? Absolutely. They would be attracted to each other. Okay, so let's say, well, how fast would they accelerate to each other? We could say, well, let's do a thought experiment. Let's take these masses out in space, just like this, a 10 kilogram mass and a 50 kilogram mass, put them a meter apart and watch what happens. Okay? This force we'll call F of G1 and then F of G2. This force creates an acceleration. The force on the mass 2, the force, on mass 1 creates an acceleration 1. So this mass is accelerated with a certain acceleration. This mass over here, it feels a different force. Well, it's numerically the same force, but it's opposite direction. We'll call it F2. Okay, F2 is heading this way, and it acts on mass 2, and it creates an acceleration also. So this accelerates with a different acceleration. Okay, this acceleration is F1 divided by m, which is the force is 3.33 times 10 to the minus 8 newtons divided by 10 kilograms. So this will be 3.33 times 10 to the minus 9 meters per second squared. So it will accelerate at this rate, 3.33 times 10 to the minus 9 meters per second. This acceleration over here is going to be different. This acceleration will be F2 divided by m2. Again, that's 3.33 times 10 to the minus 8 divided by 50 kilogram. So this would equal 3.33 divided by 50, 6.6 times 10 to the minus 10 meters per second squared. Okay, so both these masses would start to accelerate toward each other. They would accelerate at a different rate according to the masses. This would accelerate a little bit faster. This would accelerate a little bit slower. But they would accelerate right toward each other out in free space, assuming there's no friction to hold it back. Okay, eventually they would come together and boom, they would hit each other. It would take some time. We could calculate that. We won't do that right now. But you can see how this operates. Now, look at, let's consider the gravitational attraction of the Earth. Okay, let's consider the Earth. It's a big round blue ball, And here you are standing right here in Raleigh, North Carolina. You're standing right here, and you're a certain radius from the center. Okay? So here you are, and you have a certain mass, and we'll call it m. We'll call it the mass of me. Mass of me. Okay. And here's the mass of the Earth. Okay. Now we're going to take all the Earth, and because of the symmetry, what we can do. And this is exactly what Isaac Newton did. He took because of symmetry, and this is where he really had to use his calculus. He used calculus to prove to himself that all the mass of the Earth could be considered to be located right at the center. It took him a while to convince himself of that taking all the mass of the Earth and assuming it acts right at the center, he wasn't sure about that, and that's really the reason why he needed to use calculus. That was one of the reasons why he needed to use calculus. Basically what he did is he summed up all the mass in this ball in the sphere, and he used calculus to add it all up, and what he found and he thought it would show that it acts like it's acting just the equivalent mass acting right at the center, and it did. His assumption was correct, and he used calculus to prove it. So what we're going to do is we're going to take all the mass of the Earth and assign it to just the point right at the center. And we can do that. Calculus allows us to do it. We just can't prove it right now because we would have to use calculus to do it. So what you have here is you have the mass of the Earth, and then you have you right here. Okay, so let's look at the gravitational attraction between the Earth and you. That's standing right here. Okay, the force of gravity equals big G times the mass of the Earth. I'll put me times the mass of me. Whoops, I'll put me. Divided by r squared. Okay, now, remember big G is 6.67 times 10 to the minus 11 Newton times meter squared per kilogram squared. Okay, what's the mass of what is the mass of the Earth? If you look in the center of your book, or excuse me, the front cover of your book, the mass of the Earth on it has the masses of all of the planets. It says the mass of the Earth is 5.98 times 10 to the 24 kilograms. That's a lot of kilograms. 5.58 times 10 to the 24 kilograms. And what is this radius? The radius of the Earth. The radius of the Earth from the center. This will be the mean, or the average radius of the Earth from the center out to kind of the average elevation of the Earth. The radius of the Earth is 6.38 times 10 to the 6 meters. 6.38 times 10 to the 6 meters. That's the radius. Okay, now I'm going to take this. Let me just move over here a little bit. So the force of gravity, the gravitational traction between you and the Earth is G times the mass of the Earth times the mass of me, or you, divided by the radius squared, the radius from the center to where you are on the surface. And that's the force, and we can say that that's equal to ma, where m is you, or me, the mass of the mass of me, or the mass of you. So remember, we're looking at this and we're saying that this is going to cause a certain acceleration of u right here. And this is acceleration due to gravity. Okay, so this is the gravitational acceleration that is a result of the gravitational force, F equal ma. And the force is the force of gravity. Do you understand? So all we're doing is we're saying, we're taking F equal ma, which is true for any kind of force, and we're saying this force is really supplied by the gravitational force, and it's equal to mass times acceleration. And we're figuring out what's the acceleration of u standing here on the surface of the Earth. Okay, so notice we have this equation. The mass of me, or the mass of you, cancels out. Okay, and what we have is that the acceleration due to gravity equals big G times the mass of the Earth divided by r squared, the average radius of the Earth. So let's go ahead and put these numbers in. Okay, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. Okay. Divided by the radius squared. Okay, divided by the radius squared, which is 6.38 times 10 to the 6 meters squared. Okay. And so let's take this and let's multiply this out. Okay, we have 6.67 e to the minus 11 g times the mass 5.98 e to the 24 divided by 6.38 e to the 6. We have to square that, then divide, and what I get is 9.799, which will round up to 9.8, and we know the units are meter per second squared. Isn't that amazing? This is a number that we've always been using of 9.8, and it turns out you can derive it theoretically using this equation, which as you should. Now let's look for a second at the units. I'm going to erase this right now. Okay, I'm going to erase this just so we can look at the units. The units here look a little confusing. I just want you to convince yourself that this really works. We have the units of Newton times meter squared divided by kilogram squared times kilogram, all divided by meters squared. Notice the meter squared, these meter squares cancel out. One of these kilograms cancels with one of those kilograms, and what we're left with is Newton divided by kilogram. Now what's a Newton? A Newton, remember, F equal ma. 1 Newton is a kilogram times meter per second squared, the acceleration, divided by kilogram, which cancels out, which leaves us meters per second squared, which is an acceleration term, so the units work out right. So what that means is that the acceleration that we talk about here, which we say is 9.8 meters per second squared, which is the same as 32 feet per second squared. This acceleration, what is this acceleration from? It's acceleration from the Earth's gravity attraction with whatever object is up here, either you or a dog or a tree or a ball thrown in the air. Essentially, if we throw a ball in the air, we throw it even a couple hundred feet up in the air, the radius really hasn't changed all that much compared to the radius of the Earth. So the force of gravity stays essentially constant. It varies just a tiny little bit, which means that the acceleration stays constant. It varies just a very little bit. So the acceleration that we talk about is really because of the gravitational attraction from us and the Earth. Again, it's really just a result of F equal ma, and the force is the force of gravity, gravitational attraction of the Earth, and that's given by Newton's laws. And the acceleration we feel is the acceleration due to gravity. So, okay, let me see where we are in the book here. We're on page 231, and we've gone to 233, 234, and we've done circular motion. And there's only one more thing. Let's see here. We're only going to look at one more example, and that's on page 238. And that would look at what we're going to look at. We're going to look at this, but applied to a planet. Okay. In fact, I'm going to make up a problem. Let's see. Let me look in the front of the book here. Do we have... Yes. Okay. Look in the front of the book here. We have the mass of the moon, and we have the distance from the Earth and to the moon. So we can use that. This is going to be a made-up example, but it's going to be very similar to the example on page... what is the page? Is it? Example 7.6, where it talks about how fast does Mars travel in its orbit around the sun. Okay. What I'm going to do is we're going to do the same thing, but we're going to look at the moon, and instead of the Mars around the sun, we're going to look at the moon around the Earth, which is actually what Isaac Newton did, I think, first. So let's look at the physics, laws of motion of the moon orbiting around the Earth. And we know from just regular astronomical sightings of roughly what the period is. The period is how long does it take for the moon to orbit around the Earth. We know about what that is. That's about 30 days. That's about 1 month. So let's see if we can calculate that. In fact, we should be able to. Here's the Earth, and here's the moon. And as we know, that's a bad drawing, but the moon orbits around the Earth, and we have the radius here. The radius is given, again, the mean radius. It varies a little bit. It's not quite circular, but it says that the distance from the Earth, this radius is, according to the front of the book, is 3.84 times 10 to the 8th meters. 10 to the 8th meters. Okay, actually, the orbits are slightly elliptical. In one of the labs, we'll talk about Kepler's laws of motion. Unfortunately, Kepler's laws of motion are not described in the chapter 7, but one of the special labs I have, actually in this chapter, there are two labs. There's the first lab, and then the second lab is really more just of a numerical calculation lab, where the main focus of that lab is to really focus on Kepler's laws. Kepler's laws are so important to exactly what Newton was doing. It's unfortunate that the book doesn't cover Kepler's laws, but we will cover Kepler's laws in the second lab for this chapter. We're not going to talk about that right now, though. Here, let's look at this. Okay, we know that there's a force of attraction. There's a gravitational force between the Earth and the Moon. Obviously, that's the force that keeps the Moon in orbit. So this force of gravity supplies, if we consider that the Earth is stationary and the Moon revolves around the Earth. We know that's not true, but for the moment, let's just make that simplifying assumption. We know that the force of gravity between the Earth and the Moon is, let's see, can you all see this? Is G, the mass of the Earth, times the mass of the Moon, divided by the radius squared, and this force of the Moon is equal to the mass of the Moon times the acceleration.